Hello, listeners. Welcome to the 7th episode of the Unlocking the Energy Trilemma podcast with our hosts Ravi Krishnan and Jose A. Martinez, JAM. Today, Ravi and JAM speak with Mike Caravaggio, Director of Thermal and Hydro Fleet at EPRI. Previously, Mike ran integrated chemistry solutions, serving the power and water industries, and held engineering, supervisory, and management roles at Ontario Power Generation, a Canadian-based utility company. Ravi, JAM, over to you.
Thank you, Ava, and welcome, Mike, to the Unlocking the Energy Trilemma podcast.
Thank you very much, Jose. Nice to be here.
So let me ask you the first question, as we do with the rest of the guests. We ask all our speakers to share with us and our listeners a fact or figure that you think is related to the energy trilemma and you want to highlight it. So what did you bring us?
Perfect, Jose. So I thought long and hard about this, and a number that popped up in my head was from a recent analysis, and it's 4%. What the heck does that mean? 4%. So I looked at the last 5 years of output in Texas, in ERCOT, where we have a significant build out of wind and solar resources. And that 4% number, that's the minimum output on an hourly basis every month, on average, from that wind and solar. So just to put that into context, we've got about 56 gigawatts of wind and solar in Texas in the ERCOT system present. And on an average month, there's an hour every month where it's putting out only 2 gigawatts. So around 4%, and oftentimes a little bit less. That's a major nugget or major crux of the challenge as we're moving towards new lower carbon resources that are variable. It's a real challenge.
Perhaps just expanding on that, Michael, obviously this poses a lot of challenges for the thermal assets and hydro assets and other baseload assets, particularly in the context of supporting solar, wind, and energy storage, even though the percentage of electricity produced, as you say, is still not as significant as the installed capacity. Perhaps you could throw some light on some real-world examples, especially in markets such as ERCOT or certain European markets that have a cross-section of such generation assets, on what some of the challenges are for the thermal assets in the realm of the small but still growing renewable portfolio.
Yeah, so let's unpack that ERCOT example a little bit more. So I said there's about 56 gigawatts of wind and solar. The average peak load in the spring in ERCOT's about 50 gigawatts. So that wind and solar on the lowest output hour, it might be putting out 2 gigawatts. On the best hours, it may be putting out 40 gigawatts on a 50 gigawatt system. Yeah. That means that there's a lot of thermal units, and that's predominantly thermal in Texas, that need to either move out of the way very quickly or come back on very quickly. Sure. And that's a real significant challenge to those assets for 2 reasons. One, they weren't designed for that. So the original intent for most of these thermal assets when they were built was baseload operation. And the second one is we're not building much of these anymore. So they're getting old. So I don't know about you, Ravi. I don't know about you, Jose, but as I've aged, if you ask me to touch my toes and come back up real quick, I can't do that like I used to. Unfortunately, power plants are a lot like that too. As they get older, if you ask them to do more, they have a tendency to throw something out, just like you or I might.
We talk about energy transition, understanding in that transition that some new energy sources will replace existing energy sources. But in the States, for example, ICF reported a forecast of a 50% growth due to data centers, electrification, and so on, 50% growth between now and 2050. So it's more like an energy addition rather than energy transition. And what you are saying that thermal power plants will be required, it seems that the market will require them for a long time.
Yeah, even before what I think is becoming a bit of a revolution here in the US and perhaps around the world with AI and the addition of demand from expansion of data centers. Even before that, though, we had indications in the US that we really needed to keep our thermal assets still operating. So I know here in the US or in Canada, we have an organization called the North American Electric Reliability Corporation. They're responsible for bulk energy system reliability, for the electricity system reliability. They look at reliability on seasonal points, so summer and winter, as well as long term. One of the things that they've been highlighting for many years now is that we're retiring thermal assets faster than we should for reliability, both in the summer and the winter and in the long term. That's been occurring for 6, 7, 8 years. Now we're starting to see load growth, which is making it even more complex and even more of a challenge here in the US.
How do you envision the role of energy storage, especially in light of all you said? A lot of markets recently, and I'll quote India, for example, which had largely switched over to a renewable argument over the last 6 to 8 years, where they had pretty much stopped the commissioning of any thermal assets, and basically any new capacity that was coming online was largely renewable assets, until a few months ago, as they saw the economy growing at about 7 to 8%, they realized that they cannot compromise economic growth over sustainability issues. And as a result, plan to commission another 60 gigawatts of coal-fired units. And these units are expected to run for at least another 30 to 40 years. And the main argument was that the energy storage technology was not there yet from a cost, scalability, and an efficiency standpoint, and therefore they have no option but to make that choice, especially since they didn't have gas. In that context, what do you see the role of short duration and long duration energy storage in accelerating this transition?
It's a fantastic question, Ravi. So storage right now is predominantly what's scaling is the lithium ion, right? So that 4 hour, perhaps 8 hour will become economical. So that's what's scaling right now. That is an excellent storage technology for helping us with what we see here in North America, which is the summer peak. So for that summer peak, where I need to basically get some hours of power after the sun is set, particularly in August, or if I have a hot first couple of weeks of September, 4 hour storage is fit for purpose. It's fantastic for giving me that extra energy and covering that. We also have winter peaks, though. And winter peaks occur at 5 a.m. to 8 a.m. before the sun rises. And if we have a long cold spell, they can last for a while. That 4 hour solution or that 8 hour solution doesn't work so well for that winter solution, especially if I don't get an opportunity to recharge it, like I would typically in a summer situation where I'm going to have a bunch of solar the next day to recharge it, and perhaps I can use some gas assets as well. Lithium ion is good for that summer, maybe less fit for purpose for that winter, but there's a bigger challenge here, right? As we scale wind and solar, there's seasonality to this. And when we have the huge surplus in North America is in the spring. We have terawatt hours of solar being curtailed already in California on an annual basis, predominantly in the spring. What we need is a solution that can take that energy and bring it into the summer or bring it into the winter. There's not an economic way to do that currently. There's a lot of technologies that are being examined, but that's the magic one, right? Dealing with that seasonality displacement so that we can get energy from when we have an abundance from variable resources to those that somewhat tough summer, late summer peak, and that even tougher cold winter spell early morning.
You talk about scaling renewables. Let's say the whole world is investing massively in renewables, mainly wind and solar. We don't have the right long-term energy storage system yet. And at the end, this is producing a lot of volatility in the prices. Today is a hot topic in Europe. Let's say the negative prices in the market ahead. In the US, you had negative prices for 10 years in real-time markets. Are negative prices good or bad?
So I think negative prices are complex, right? So what does a negative price mean? It essentially means that somebody's got a contract's been set up or there's a tax incentive that's allowing a generator to operate at a negative, a loss in the market, but continue to operate. So they're still made whole. If it's through a tax incentive, then it's not the ratepayers paying for it. If it's through a power purchase agreement that they're made whole and they're guaranteed a certain dollar per megawatt, then that negative, the ratepayers are still paying for it. You just don't see it in the wholesale prices. And then there's also a challenge for the ratepayers when you have negative prices. It usually means that in your jurisdiction, you're paying a neighboring jurisdiction to take that electricity. As a retail player, you're not going to see that negative price, but you're going to not see a negative wholesale price. You will see that cost to send electricity to your neighbors. And I know this deeply because we had this problem in Ontario when I was growing up from a surplus of baseload generation. So we would pay Michigan or pay New York to take electricity, and that would get built into our retail rates. So negative prices are good for wholesale buyers. But you and Ravi and myself, we don't have access to wholesale markets. And we probably don't want to have access to wholesale markets. Because the ones that did, especially in Texas, back in Winter Storm Uri, there was a company called Griddy. A lot of people had access to wholesale prices there. And that negative can easily turn to a positive. And when prices went to $9,000 per megawatt hour, that company went out of business and a lot of people had very unfortunate bills. So negative prices, in my opinion, indicates a problem in the market and usually imparts a significant cost to whichever market has those negative prices for retail buyers.
Yeah, so that's a great argument, Mike. And we've been talking about some of the challenges. Just thinking ahead, how do you see the balance shifting between renewable and non-renewable energy sources over the next decade, for example? Can you share some perspective on which technologies perhaps have the greatest potential to transform the industry?
Yes, I can say what's scaling, right? And so we had wind scaling significantly in North America. Now we have solar scaling much more significantly. So we're going to be building out wind and solar. And what we're going to build to match that will essentially be looking to be fit for purpose. And in the case of thermal assets, that's typically simple cycle gas turbines. So we're seeing a lot more of those being built. They're going to have maybe a low capacity factor, but they have the ability to ramp to match that solar, which is going to have that daily cycle. We're seeing a little bit of one-on-one combined cycle as well to try to match that. But really that simple cycle gas turbine that can move really fast and has a low holding cost. What do I mean by that? You don't need to have operating staff at a simple cycle gas turbine plant. So even if I have a very low capacity factor, it doesn't cost me a lot to hold that asset. So it's going to be a lot of solar, a little bit more wind, and quite a bit of simple cycle gas turbine, at least here in the US, that's scaling over the next 10 years. Beyond that, hopefully we've done a whole bunch of stuff that some better technologies can get brought in that can essentially drive us closer to net zero in a sustainable way. They're not going to start scaling in the next 10 years.
What about this whole emergence of distributed energy resources, DERs, and a lot of the behind the meter type applications that could be a combination of solar PV plus wind turbines plus, as you said, simple cycle plus battery storage, and the customer actually going in for off-grid solutions. How viable do you think that concept is? And clearly there is a proliferation of DERs in the market, and there are various challenges that bring to the table. How do you see the role of DERs and customers going off grid, especially those operating data centers and others which are projected to grow?
Yeah, so it's a great question. So first off, I'm going to show my bias here. I'm a generation guy, central stations, I'm a little bit biased towards the old school, but I think there's a big role for DER, right? I think that there's significant opportunity for peak shaving and doing that correction. And there's a lot of opportunity for that. I know that there is some talk for data centers as being off grid, but there's also talk about them needing to be grid connected and them being a resource. So data centers, we don't have a great understanding on why they use their energy, when they use their energy, and how much flexibility they have on that. But if they have a fair bit of flexibility on when they're using the energy, or if they can move it from one data center to another, all of a sudden a grid connected data center is not just a large new load, it's also a large potential source of flexibility. I think things like that are going to be very significant going forward when we can figure out how to use these large loads a little bit better interconnectedly, build off the stuff we've already started building out in terms of distributed energy resources, apply that to these large loads, and all of a sudden we may have something that's a real benefit. I think it's part of the solution, though. I think we're going to definitely still need central generation to solve or to provide that electricity demand, but DER is definitely going to have an expanded role over the long term. From a generation guy, so even I have seen the light. Don't tell anybody I work with.
And we have regions with big amount of renewables. We have a thermal fleet, and in some occasions we have a lack of let's say energy from renewables that has to be covered by thermal. So imports and exports of electricity between regions seem very important, and interconnections between regions, not only in the States but in some countries in Europe or in many regions around the globe, are not a key priority, and developing an interconnection could take a lot of years, but it could be a kind of a storage between regions. I don't have wind now, but you have. You are more an eastern region, and then I can have more sun later. Or you have a thermal power plant that can cover my drop of renewables. So what do you think about interconnections?
Yeah, so it's a great question. And transmission has a big role to play, but I often think what's more difficult to build than a nuclear plant in the energy system? Transmission, right? And why is that? It's because it's going through many jurisdictions. It's going through many local jurisdictions. It could be going through multiple states to get, say, here in North America, we're wind rich in the central states, and we need energy on the coast. That's a lot of states. That's a lot of local communities to go through that may not see a benefit to that high voltage line going through. They may only see a cost. So that's a big driver that makes it more difficult. All these transmission lines will incur additional costs as well. So figuring out how to balance that, who should pay for that cost, and how to manage that, it's tricky. And I think the biggest hurdle, though, is that it's just difficult to get that many people to support these long lines. And that's why we see, I think, typical in the US, may take 17 years to build a new large-scale transmission line, which how many 17 years do we have before 2050? Not that many, right? So maybe 2 iterations of this.
So recently, Michael, I saw a post on your LinkedIn that looked at the assessment and relative benefits and impacts of various technologies. So many different ways you can peel the onion and achieve decarbonization. So if anything stands out, let's see what your views are.
The one I'm most, and this is a personal opinion, the most bullish on is actually the small modular reactors. Yeah, that's because we can build them. They're not going to be regionally held in. The infrastructure for them is just the build of the actual plant, right? So instead of the hydrogen, where I'm going to need pipelines, and the CO2 sequestration, where I'm also going to need pipelines, and I have additional challenges, much like the transmission of going through different jurisdictions. But SMR, we're building one, right? So they're breaking ground on the GE Hitachi BWR 300 at the Darlington nuclear site in my home province of Ontario. SMRs are a less economic way to make nuclear power than large nuclear units. So everybody goes, why would we do this? That's very much true, but you can build them in less time and you can build them for less money before you start making money, right? So a large nuclear plant could take 10 years, more often takes 20 years. If that's 10 or $20 billion you need to invest and wait for 10 or 20 years before you get your money, start making your money out, that's a huge investment, a huge risk. The SMRs, so the Darlington one, they break ground in 2025. They hope to have it commercially operated by the end of 2029. That's only 4 years. It's less capital that's locked up. If that's proved successful, those can scale, right? And this will be perhaps, so the first of a kind is always the longest, or typically the longest and the most expensive. So if we started doing several of those, we should start to see some cost reduction, some improvement in timing. So I'm not bullish on anything, but SMRs I'm excited about.
What do you think about the argument around cost? I've heard numbers like $5 million a megawatt for SMR. Do you see any reduction in that as years go by?
Yeah, I suspect there's going to be cost reduction, but the thing to remember is right now we're trying to find a marrying technology to wind and solar. And it comes back to that thing I said at the beginning, that 4%, right? I have a technology that can produce a lot of energy, but there's going to be hours where it doesn't produce much at all. And to get a 4%, so if I needed 40 gigawatts and I have basically something that can go down to 4%, I need to build 20 times that. So solar and wind are the cheapest cost of energy when they're available, but they're not always available. So the SMRs and other technologies have the potential to fill that in. And we need something with zero carbon or near zero carbon, right? CCS and hydrogen are going to have similar or perhaps even worse costs than the SMR, and we're still learning on those. The SMR, when we're talking about a GE Hitachi BWR reactor, we know those, right? We've built big ones of those for years. So I'm very bullish on those known technologies that the cost can reduce and that we can do that successfully to lower the carbon footprint of our energy system.
Mike, thank you very much for all the conversation. Let us close with a last question that we do to all our guests. If you had a magic wand and you have the chance to unlock the energy trilemma, what would you do? What would you ask?
The magic wand question, I think, is a little bit tricky for us, right? I think the magic wand for me would be for everyone to actually understand what our technologies currently can do and what it will really take to get to net zero. A real understanding, not optimistic talking, believe in it will come. My magic wand is let's get serious. Let's look at the numbers as they've generated, understand that you can get to a certain level of decarbonization with variable resources, but we can't take it all the way there. We need other technologies. We need to do the work we're doing with hydrogen. We need to do the work we're doing with CCS. We need to do the work we're doing with SMR because we need a technology that my friends at very close utility call ZELFRs. We need zero emitting, load following resources. And a ZELFR, I like the sound of it because it sounds like a unicorn type name to me because of the mystical beast right now. We don't have a zero emitting load following resource. We don't know what that's going to be. We don't know which technology is going to be cost effective for that. We need a ZELFR. So we need to be doing work on potential ZELFRs like green fuels, be it hydrogen or another, CCS, or small modular reactors, or more long duration energy storage solutions, but we need a ZELFR. And until we have a ZELFR that can operate like a gas plant currently operates at, I don't know if we get to net zero. So that's my magic wand. Let's be serious. Let's not be too optimistic.
I think we'll have to touch with that magic wand a lot of politicians all over the world to modify their pitches, but let's cross fingers it works. Okay,
Excellent.
Mike, thank you very much indeed.
Thank you very much. And I think ZELFR is a term that we'll remember for some time now. It's certainly a new terminology for our viewers. Thank you so much for your time. today. We look forward to having you again on the show to discuss more on such topics. And thank you to our viewers as well for joining us. Thank you very much.
Thanks, guys.
Thank you.
We hope you liked this conversation. Follow us on LinkedIn or subscribe for free to the podcast on the platform of your choice, Spotify, Amazon, YouTube, or Apple. Because in the next episode, Ravi and JAM will speak with another industry expert who will help us to unlock the energy trilemma.